So this video is the first in a series of extra helping videos that I'll create for those of you who still feel a little bit unsure with the elements of the vectors unit that we've just completed. So the first thing I'd like to do is I've given you a line here, and I'd like to take you through step by step how to transform this normal vector representation of the line into the vector equation of this same line. And we have two possible methods for this. I'll show you both because I think it's helpful for your understanding to see both. And you can then choose the one that you prefer to do this yourself. So, method 1. What I'll do in method 1 is I will find all four forms of the line. So, I will say, first of all, I'll find the easiest other form of the line, which is the implicit form. Now, you should be familiar by now with the fact that this capital X means any point on the line. And so it can be expressed as little x, little y, the coordinates of any point on the line. So if we multiply this out using our scalar product now, we have 3, 4 times little x, little y is negative 1, which means I have 3x plus 4y is equal to 1. And all I've done there is the standard scalar product, the top components multiplied together plus the product of the bottom components, and that is always equal to 1. And it's also worth reiterating that both of these equations, they're exactly the same equation written in different forms, and all points on the line satisfy this equation. That's worth noting. Okay. So now I have the implicit equation. So this one is the implicit form. I can easily find the explicit form just by rearranging. You'll remember that the explicit form is in the form y is equal to mx plus c, or kx plus d in the German-speaking world. So all I need to do is rearrange this implicit form to bring it into this form. So I have 3x plus 4y is equal to 1. I want the y on its own on the left-hand side. So first of all, I'll take off 3x to get 4y is equal to minus 3x plus 1. And I will divide by 4. And I will then say y is equal to minus 3x over 4 plus a quarter. And this is our explicit form, the equation of the line that you should be very familiar with from last year. So I've got 3 of our forms. This is 1, 2, 3. All that's left is to find the vector equation of the line using the forms that I have. So I know that the vector equation of the line is of the form all points on the line satisfy this equation, where I have the point, any point on the line, it doesn't matter which one, plus the direction vector multiplied by a parameter. So I start from a point and I travel along the direction vector as many times as t tells me to, and by doing this I can get to any other point on the line. If t is negative, then I go in the other direction to get points in the other direction on the line. So a point we could easily find through any of our equations. We just need an x and a y that satisfy any of the 3 equations that we have. So what I'll do is I'll take this one. So for the point, I will take 3x plus 4y is equal to -1. Oh, I missed my negative off there. And here, and therefore here. Sorry about that mistake. Hopefully you noticed it and corrected it in your own notes. I'd missed a 1 somewhere, a -1, sorry, somewhere. So I need to find an x and a y that work in this equation, and then I have 1 point on the line. And it doesn't matter which point it is. If I start here and travel in that direction or that direction, I can reach any point on the line. Similarly, if I start here and travel in that direction and that direction, I can still reach any point on the line. So the easiest one, I would say, would be if x were equal to 1 and y were equal to -1. Because then I'd have 3 minus 4, which gives me the -1. So these work and they're easy. You could have equally chosen x as 0 and y as being -1/4, or x as being -1/3 and y as being 0, for example. It doesn't really matter, but I've chosen these two because they work. So we have our point is 1 minus 1. Then we need our direction vector. Now a way of doing this is find a second point on the line. Let's call this one B and this one A. Then I can do B minus A gives me the direction vector from A to B, and that would be a perfectly acceptable direction vector for this line. So I have this point on the line which I've called A. So let's say that B is, we could take x as being 2. If x is 2, then that's 6. It doesn't work so well. It would give me a fraction, and I wanted to avoid fractions. Instead, let's take x as being 5. If x is 5, then I have 15 plus 4y is -1. So 4y is -16, and y is -4. So I've got 5 and -4. This is the second point that works. You could have equally well taken anything for x and just found the y out. It really doesn't matter what the point is, but I'd recommend avoiding fractions where possible just to make your calculations easier. Then we know that the vector from A to B is B minus A, so we have 5 -4 minus 1 -1, which gives us 4 minus 4 minus -1, 4 -3, which is a perfectly acceptable direction vector. So I can write the form now as being x is equal to 1 minus 1, and here I could have equally well inserted 5 -4 plus t times 4 -3, and you'll notice that I can write the t before or after the direction vector because multiplication is commutative. It really doesn't matter, but it's conventional to write it beforehand. So I found the vector equation of my line using the first method that I mentioned. Now the second method is in some ways slightly easier. We still need to find the point in the same way. So I'll use the point from the one that we had before. We have 1, -1. So I can put that in straight away. Now to find the direction vector, directly from the normal vector representation, I know that in my normal vector representation here, 3, 4 times x is -1, I know that this vector here is a normal vector for the line. Because that's why it's called the normal vector representation. So, a direction vector for the line, let's write this down, not in my handwriting. A direction vector for the line is perpendicular to the normal vector for the line, or to any normal vector. If you imagine that your line, if your line goes like this, then a direction vector for the line goes in this direction, or of course in this direction, and the normal vector to the line, because it's perpendicular to the line, will always be perpendicular to those vectors. So my only job here, let's move it out of the way, my only job here is to find a vector perpendicular to the normal vector. And this then will be a perfectly acceptable direction vector, because any vector that's perpendicular to this one will be a direction vector for the line. And to find a vector that's perpendicular to the normal vector, we need to find one for which, if we multiply it by the normal vector, the scalar product gives the answer 0. So we learned a trick where we can just flip these upside down and make one of them negative. So I could use negative 4, 3, or 4, negative 3. Because if I take the scalar product of this one with this, I get 0. Or if I take the scalar product with this one with this, I also get 0. So either one, it doesn't matter. They're both direction vectors. So I could take, let's take the first one, negative 4, 3, as a direction vector for the line. And you'll see actually the other direction vector that we found in that in that method is exactly the same as the direction vector we found in the first method. So if you're comfortable with normal vectors being perpendicular, then this is probably a quicker way to do it. I hope that this video has answered any questions you have about transforming things this way round. I'll now make a second video which does things in the other way round, in which we have the vector equation of the line, and then we need to find the normal vector representation and all of the other forms as well. If you still have any questions, then please come and see me individually.